Thank you very much, Tony, for the introduction. And yeah, of course, it's a great pleasure for me to give this talk during the program in memory of Fred. And of course, thanks the organizers for inviting me and giving me this opportunity to talk. So yeah, I'll talk about permutohedral complex and complements of diagonal subspace arrangements. And of course, as all of you, I'm a great admirer of works of Fred. And these works are certainly behind this subject, behind this, maybe not in a precisely explicit form, but I'll tell you some story about that link, how it links to Fred Cohen's work and how he influenced all this study. So, but before I do so, let me just briefly run through the definitions. So what's a diagonal subspace arrangements and why they're interesting. So you have an arrangement. Well, an arrangement is a finite set of affine subspace in an affine space, either real or complex. And there are two particularly interesting classes of arrangements, coordinate subspace arrangement and diagonal subspace arrangement, in the sense that they both are encoded by simplicial complexes in basically the same way. So a coordinate arrangement consists of coordinate subspaces. Like a coordinate subspace is just obtained by setting some coordinates to 0. And then this is defined by a subset of M letters. And then you can easily guess that the underlying combinatorial structure here is a simplicial complex. So whenever you have a simplicial complex on finite simplicial complex on M element set, you can define the corresponding real coordinate subspace arrangement. You just take those coordinate subspaces which correspond to non-simplices. For some reason, non-simplices is better to use non-simplices rather than simplices. I'll tell you in a second why it's so. Because, well, although if you take an arrangement, you can, as a set of subspaces, there can be inclusions there. So, like, you can have a line included, like in a flag, in a two-dimensional plane, and that is not somehow captured by the simplicial complex. But if you look at the complement, you take the union of all subsets and take its complement, then that space is there as many different spaces as there are simplicial complexes on M letters. So that's why we use this notation UR of K. So basically, the complement of a coordinate subspace arrangement is in one-to-one correspondence with simplicial complexes. Okay. And then you can do the same. This U of K is somehow the notation coming from toric geometry. Maybe I'll mention that in a second. Yeah. So then you can do the similar business with diagonal arrangements. The diagonal arrangements consists of diagonal subspaces, where diagonal subspaces is just obtained by setting some coordinates to be equal to each other. And then again, here is a subset, and again, there is a simplicial complex. So whenever you have a simplicial complex, the difference is actually here in the previous slide, the coordinate subspace arrangement, you can take a simplicial complex on the set with ghost vertices probably, and it still gives you a coordinate subspace arrangement. With diagonal arrangements, you need to actually to be the simplicial complex on the vertex set. Every one element subset has to be a vertex. So that a tiny difference here, but anyway, so whenever you have a simplicial complex, you can define similarly the diagonal arrangement and its complement. And as I said, that correspondence you can associate a coordinate subspace arrangement complements with a simplicial complex, or associate a diagonal subspace arrangement complement with a simplicial complex, and that's a one-to-one order preserving correspondence between simplicial complexes on let's say on the vertex set M and coordinate or diagonal arrangements complements in Rm. And you can do the same the same thing, just to fix the notation, we'll also occasionally consider complex case, then you have everything in complex space, and so that we denote this with complex subscript diagonal arrangement and diagonal arrangement complement. All right, so now I have probably reached the point where I can start telling you some stories, and yeah, maybe yeah, it's we don't need to do anything with the light, I think, at the moment. Okay, so why the spaces are interesting? So I mean, back in around 1999, Victor Buchstaber and I, we realized that, well, you can try to understand the topology of these complements of a coordinate subspace arrangement. So let's say this is coordinate, and so that's you say in the complex case, and we understood that actually this is an open. It's an open subset in CM, right? So and it deformation attracts onto something compact, which we now call the moment angle complex. So that's a deformation attraction. For every simplicial complex, you can build up, using some inductive process, you can build up this deformation retraction. It's basically something like you throw away a point, a zero from CM, that's an example of coordinate subspace arrangement complement, and then you retract that onto a unit sphere, which is an example of the moment angle complex. And then that generalizes to arbitrary K. And well, that space is interesting from many perspectives. First of all, it's a arrangement complement, and there is a by that time there was a great theorem, Goreski and McPherson, which identifies the topology of an arbitrary arrangement complement, but it only tells you how the Betti numbers look and in terms of the combinatorics of the underlying poset. And using that approach with the moment angle complex, because that is a very nice compact space, it has a nice cell structure, and which you can use to actually identify the cohomology and the cohomology ring. So that we were able to calculate the cohomology ring of this one and also compare that with the general Goreski-McPherson formula, and it was some nice interplay between combinatorics and topology using the Alexander duality and so on. So, and also, of course, yeah, that space is not just an arrangement, it features in toric geometry as a there is a quotient construction of toric varieties which starts with this space. I'd rather say it's in a slightly restricted way when it's not just determined by a simplicial complex, by a special simplicial complex which underlies a fan. In this case, a complete simplicial. Well, okay, let's probably keep that notation. And that by taking quotient by some quasi-torus, what is called in this toric geometry, you get all toric varieties B sigma. And there is also a simplicial version of this construction known as a symplectic reduction. And in the symplectic version of this construction, that instead of this open subset, you get something which is called the level set for the moment map. And this level set for the moment map is precisely one of the interpretation of this moment angle complex. So that's, and then again, this what they call universal torsor in toric geometry, that complement of a coordinate subspace arrangement deformation retracts onto this compact set. And because of this decomposition in this circle, you can calculate it cohomology based. So that was one of the motivations to consider that, or at least two motivations from the general arrangement perspective and from the toric geometry to consider these complements of coordinate subspace arrangements. And also, yeah, I mean, This complement is also an example of a toric variety itself, right? Also, it's non-compact, it's open, but it's still non-singular, and it has an action of algebraic torus on it. So it's an example of a non-singular, but not complete, not compact toric variety. And this, in this setup, it was studied in the work of works of Matthias Franz, and he also calculated this cohomology of these open toric varieties and obtained this similar description, same basically description in terms of the Tor module of the Stenley-Reisner. So that what was about coordinate arrangements, and then okay, so then we realized that okay, there is another class of arrangements parameterized by simplicial complexes, which are diagonal arrangements, and they are by no means they are less well known. I mean, the most famous one is that you just throw away all diagonal subspaces, diagonal hyperplanes. I wanted to say that's in that notation of diagonal. That's just DC of m points. So that's a diagonal arrangement complements corresponding to a simplicial complex consisting of m disjoint points. And then this by the famous theorem of Arnold. This is the K-pi1 space for the pure braid group. And also in around 1999, there was a paper of that diagonal subspace arrangement also were studied by in particular by combinatorial commutative algebraists, and there was a theorem due to Pieva, Bulgarian Pieva, Reiner, Welker, which tells you in a way somehow resembling the situation with a coordinate subspace arrangement, but in a bit more subtle way, that when you calculate the complement, the cohomology of the complements of the real diagonal subspace arrangement, then you get something like the Tor of the Stenley-Reisner, but in the different Tor. Instead of calculating, like in this case, you calculate the polynomial, the Stenley-Reisner as a module of the polynomial ring and calculate Tor, and it's finite dimensional over K. This one is infinite dimensional, and you need to pick up some component of that, like I minus M, and then that's external grading, and then you need to pick up some multi-graded component. Well, it depends on how you grade the space rings. At that time, I mean, topological grading is like the even numbers. Let me put a 2's here, or maybe, okay, it doesn't matter. 2. But that was a theorem that somehow relates the cohomology of the diagonal subspace arrangements with a homological invariant of the phase rings. And that was similar to that result mentioned by many people before, including Yelena, about that the cohomology of the coordinate subspace arrangement is also some kind of Tor, right? So then, well, by that time, we realized that, well, I mean, that's all happened around this year. So we learned about this theorem, and then, well, by that time we knew that this K of K, the phase ring, is the cohomology of what we now call the Davis-Januszkiewicz space, which is here. Oh, really? Oh, I haven't realized that. Yeah, sorry. I thought it. Oh, yeah.
Now you can see it. Could you start again?
Yeah. Okay. Yeah, sorry. So okay, yeah. So this is the Davis-Januszkiewicz space is a polyhedral product of point to the power k. And so by Adams-Escobar construction together with some formality result on this space, you can identify this as a subspace in the cohomology of loops on the Davis-Janusz-Killish space. So there are already loop spaces here, but at that time we just mentioned that, and we thought that that was a just kind of peculiarity, mere with no big consequences, just to somehow put that result of Pierre Welker into the context of this Tor things, the cohomology of Stanley-Reisner rings, and also cohomology of what is now called polyhedral products. But we didn't much develop that. But then Natalia Dobrinskaya, in Moscow, Natalia Dobrinskaya, she was at that time the student of Victor Buchstaber. That was already around 2005. Yeah, no, exactly in 2005. Natalia Dobrinskaya, she went, that's where Fred comes. So she went to this Tokyo conference mentioned here many times in the memory of, sorry, it's the 60th birthday of Fred. At that time, yeah, I probably met Fred at some conferences, but we didn't have contact with him. But Natalia went there and she talked to him intensively in Tokyo, and then she of course knew about this kind of link, and then she came back and that she told me, oh, these all are configuration spaces. This diagonal subspace arrangement are special configuration spaces, and there are lots of course, great results about this, and somehow we should incorporate that, and we should use that to understand this link more in more detail. And so she actually, well, that's the idea is very simple. If you look at this diagonal subspace arrangement complement, then it is a configuration space, right? So this one, the first one is just a configuration space of m points on a plane. And when you do some more complicated diagonal subspace arrangement, it's still kind of a configuration space, but with labels. Somehow you do not throw away all. Sometimes here you do not allow the points to collide. But if you throw away some diagonal subspaces, not all of them, then that means that you allow some points to collide. And this is somehow governed by the simplicial complex. So you have a configuration space labeled by simplices in a simplicial complex. That can be made precise. I'm not going to tell this, but that somehow puts this diagonal subspace arrangement into the context of configuration spaces, and therefore you can use all these techniques developed. Yeah, so, and she did some very nice work on identifying the cohomology of this diagonal subspace arrangement with the cohomology of labeled configuration space, so that so she actually came with this understanding that this is some component of this labeled configuration space. And she then further identified with some special up to homotopy equivalence with a, you can make this, that's standard in this configuration space here. You can replace this configuration space by a monoid up to homotopy, and then you can use the homotopical techniques to build up a DJ model for the complement of a diagonal subspace arrangement. That's what Natalia did, and unfortunately she didn't pursue that to the level when it can be actually made into nice precise statements with proof. Her last preprint was about 2009, in 2009, and after that, yeah, unfortunately she stopped doing mathematics. But I mean, that thing baffled me since that time. And I mean, after that, of course, we established very close contact with Fred and with Tony, with Martin, and with Sam Gittler. All that stuff grew into what is now called the polyhedral product theory. Then that famous BBCG decomposition appeared, and we started talking to Fred regularly, but that was a different story, right? That's polyhedral products, and that's not the original point where we actually felt the influence of great mathematics done by Fred. So then, I mean, I had that in mind, and I mean, from time to time, I suggested that problem of understanding the cohomology ring structure of the diagonal subspace arrangement, and then I forgot to mention, but I'll mention it now. I have this very good student, Vsevolod Trill, and we somehow did, we looked at it from a slightly different perspective. And yeah, I'll stop writing things now. So back to the slides, yeah. So, and what I'm going to tell now is not precisely in this context. So that is yet to be understood. The relations to configuration spaces and the way how you can extract the ring structure from this isomorphism is yet to be understood. So what I'm going to tell is a bit different perspective, but still it certainly needs to be developed further. So okay, so why how we can try to attack this diagonal subspace arrangement complements using the same strategy as for the coordinate ones. So why that works, that upper line? So because we have a coordinate subspace arrangement, a complement which is open subset in CM, but then we deformation retract onto something compact which has a nice cell structure. And in the complex case, that's a moment angle complex, and in the real case, I'll probably write the last line. That's UR of K. Deformation retracts onto what's called the real moment angle complex, which is D1 S0 to the power K, which is a subcomplex in the M cube. A special cubical subcomplex is somehow cut off from the cube by your simplicial complex. And that's also deformation retraction. So you deformation retract onto this, and then you calculate cohomology of that one using its cell structure. So that worked perfectly well with a moment angle complex. So you get nice DJ model, that Kosul type DJ model, which basically describes the cellular diagonal in the moment angle complex, and then you calculate this cohomology of this DJ model. You get the Tor, and that everything is very nice. Here it's a bit more messy because I mean the cellular model you get is non-commutative, but you still can do lots of calculation with products, right? So there are three main, well, two, I don't know, depending on the point. So you get deformation retract this thing onto something compact, which has a nice cell structure as a subcomplex in the cube, and then you build up a DJ model from that. That's how it worked for coordinate subspace arrangements. How you can try to apply that to diagonal subspace arrangement is the next questions which we're only now starting to grasp, right? So let me just go briefly through this in more detail. Through this procedure. It's called the diagonal approximation was built up by Litzai. And so this is a real moment angle complex. The polyhedral product of D1 is 0. As I said, it's a subcomplex in the M-dimensional cube. Yeah, so now there is no light. Okay, good. So yeah, so this is a real moment angle complex, and there is this deformation retraction. And okay, so now from this, so now you can, instead of studying this complement, you study this compact model, and then you decompose it into cells, very simple cells. So each segment in the cube has three. It's a simplicial complex actually, so but it has three cells. The two vertices denoted by T subscribed I and just Ti, and this one simplex. And so that a cell in a cube is just the product of those things, and you just encoded that by this kind of sign vector like this, a product of cells. And so each cell in the cube is just encoded by two non-intersecting subsets on M indices. And the cells in this real moment angle complex, the cubic complex, are specified by the condition that this set of UI cells is a simplex. Okay, that's fairly simple. But there's some messy indices here, but that's the idea is, of course, just every cell is a product of points and open segments. Okay, so then it's better actually to use some, well, of course, then you can identify the corresponding cellular chains, and then it's better to change the basis so that instead of, so you keep TI, but instead of TI underscore, you use TI minus TI underscore, which is the boundary of the one cell. But then again, you have the cellular chains. We drop this zero dimensional, this T bit, so you just sigma and tau. And then this is the basis in the cellular chain of the cube. And you can look at the dual cochains with upper indices. So these are just UI star per star and so on. So these are dual cellular cochains, and then the cellular, you have the cellular differential, which you can easily understand. And yeah, after that you have this. Now you want to calculate the cup product, and then you, of course, because it's zero dimensional, there is something. Oh, sorry. Oops. Something messy happens. So when you multiply them, this cochains, you see that first of all they are not commutative, and there are lots of idempotencies there, and that the whole algebraic structure is not as nice as in the complex case. But nevertheless, you can build up this DJ model from the cellular chains, and using the diagonal approximation or just Whitney formula, you build up a DJ structure on these cellular chains, and then you get a DJ model. So that's just the cellular cochains of RK with this multiplication. And that gives you a DJ model for the complement of a real subspace arrangement. So the idea is like you do it with a complex case, you use cells, but when you calculate multiplication, it becomes a bit more complicated. So, okay, so then you can dualize that, or you can write it down instead of chains, in terms of chains instead of cochains, and then you get the diagonal. The diagonal on the cellular chain algebra of the cube. And well, it has this a bit messy but explicit formula. So on the top dimensional cell, for instance, it's like this. So this is lead psi diagonal. And now, okay, so you want to apply the same sort of strategy to diagonal subspace arrangement complements. And then you understand that instead of the cubical complex, you need to consider permutohedral. And that's what the permutohedral complex is about. So you build up a complex out of a permutohedron in the same way as you do with cubes and real moment angle complex. So let me remind you that the permutohedron is just the complex convex polytope obtained by taking convex hull of all permutation of a set of M indices. So look at it, has M factorial vertices. It's easy to understand that every permutation is a vertex actually of this polytope. It's M-1 dimensional because they all sit in a hyperplane. The sum is constant. And then there is a classical result about how you describe the phase structure of this permutohedron. The phases of dimension P, so like the vertices are just permutations, and the phases of dimension P are ordered partitions of the set into M minus P non-empty parts. So like if P is 0, you split it into M non-empty parts, and that's just a permutation because it's ordered. And the the facets are just partitions into two parts, but ordered still. And then you can describe inclusion corresponds to refining. So inclusion of a phase occurs whenever the ordered partition corresponding to a smaller phase is obtained from the partition corresponding to a larger phase by refining. All right, so that's how you add it. That's a very good exercise in convex geometry actually, but that's a very nice description in terms of partition. So we denote this face corresponding to the ordered partition by this f of this. It uses bars for some reason, yeah, because it's related to the bar construction, of course. And whenever you have, we also assume that whenever you have a part here, like then elements in every part are, when we write it like this, are increasingly ordered. So that's how you define faces of permutohedron. Then, okay, then you use this very simple idea. So whenever you have a simplicial complex, you can define the corresponding permutohedral complex by just considering only those faces corresponding to partitions in which all parts are simplices. And then there is a theorem which is proved in a kind of similar way you do with this one, or with a complex by doing some inductive process, but a bit more involved and technical, but nevertheless you can do it. So that's exactly the compact model for the diagonal subspace arrangement complement. So the diagonal subspace, real diagonal subspace, that's so far it only works for real diagonal subspace arrangement. So I'll tell about complex later. Yeah. 10 more minutes. Okay, so that's you have similar kind of deformation retraction. So you have now this is a compact model for a complement, and you can try to understand cohomology from this. So let me draw some picture and example. So if you have a complete graph on m vertices, so it's one-dimensional simplicial complexes with all edges present, but no higher dimensional simplices. Then this permutohedral complex is the face of cubic faces of the permutohedron. In the permutohedron, there are some faces which are cubes. And this is precisely what you take when your K is one-dimensional, so is one-dimensional complete graph. So this is the bluish ones are the square faces, and so the union of all the one skeleton and this, you take the one skeleton and you take this 6 squares, but you omit 8 hexagons. Yes. So this is your permutohedral complex, and you can see actually that like the dr of k in this case is just R4 without like x1 equals x2 equals x3 and then x1 equals without 4 lines obtained by, there are 4 lines obtained by setting 3 coordinates to be equal to each other. You have to throw away those 4 lines, and you can see on that picture those 4 lines, they somehow cut this opposite hexagonal faces. And you remove them, these 4 lines, and the complement contracts onto this permutohedral complex. Okay, so deformation retract, that's how it works. All right, so as I said, that is also a similar procedure. I mean, there is no such nice parallel between real and complex diagonal subspace arrangement as in the case of coordinate ones, because like you can think of every complex coordinate subspace arrangement as a real coordinate subspace arrangement by just forgetting and you have the complex coordinate means equals 0 means that its real part and imaginary part is 0. So that on the level of simplicial complex, that corresponds to this famous doubling operation that was studied in the works of Barry Bendersky, Cohen, and Gittler. Yeah, and so that you can somehow flip between those two. In the case of diagonal subspace, it's not like that, right? Because I mean, it's when you have 2 complex coordinates equal to each other, that's a different condition. You can just, in order to pass to real ones, you have to do some. So that basically what you do, you consider permutohedron in the twice-dimensional in the real vector space, and you pick up that you consider the splitting of the 2m element set into m and m prime parts, and then you can prepare some permutohedral complex which is not as easily described in the real case. So you throw away the relative interior of some faces still, And this corresponds to those partitions for which that like you throw away something corresponding to non-simplices, but here you have simultaneously that non-simplexes must be contained in both I, and it's like imaginary part has to be contained in some UIs. But that's still some permutohedral complex, but a bit more complicated and described. So that you can do complex arrangements as well. And then you have this homotopy equivalence. All right. So now, okay, so that's how it looks geometrically, how to build up a model for that, a DJ model, algebraic model. Well, you recall this bar construction. And yeah, I forgot to say that here, actually, that this is how it was stated in the work of Pierre, Reiner, and Welker, and how we stated that when we try to relate it to the loop spaces on polyhedral product, but it actually, there should be exterior Stanley-Reisner algebra instead of the standard one for some good reason. Yeah, so I mean, it doesn't affect the theorem because this graded component is still the same, but it's actually, when you consider that relations with a configuration spaces, then you should consider this exterior Stanley-Reisner algebra. Yeah, that's I'm not going to go into details there, but we just take. Yeah. So that's so now you take this exterior Stanley-Reisner algebra, which is a quotient of the exterior algebra by the same monomial ideal corresponding to non-simplices, and then if you look at its bar construction, then its basis corresponds to precisely this things between bars are monomials in your in the exterior Stanley-Reisner algebra. You can write down the differential, of course, combinatorially, and then you actually you can instantly understand that it looks like the cochains on this permutohedral complex. So the cellular cochain complex of this permutohedral complex is isomorphic to this multi-degree one-on-one component of the reduced bar construction of the Stanley-Reisner. So, well, the proof is actually very simple. The idea is very simple. You map it like you actually do for the moment angle complexes when you want to identify the cellular cochains of the moment angle complex with a Kossur algebra. That you get it. You do it on the level of cells, identify the basis, and check that it works well with the differential. So it's like similar here. So here you have this face corresponding to a two-ordered partition, that the dual cochain, and you map it into the corresponding basis element of the bar construction. So it's isomorphism of K module by construction. It makes basis to basis, and then you can check the differences. That's quite a complicated check. You need to, but thankfully there is in the work of Milgram, there is a description of the boundary in the cellular chain complex of the whole permutohedron, right? So using this Milgram's formula, we can actually prove that that map respects the differential. So, and as a corollary, of course, you get this version of theorem of Pierre, Reiner, and Welker, but we properly put exterior algebra instead of the polynomial one. But one of the reasons is that it's coming from the bar construction for the exterior algebra as a polynomial, and it also works well with this interpretation of configuration spaces. So that's how the cohomology of these diagonal arrangements look like. And now, okay, well, then you want to understand the ring structure, and of course, then this doesn't help much because it's just only one multigraded component. There is a multiplication in the bar construction in the store, in the big Tor, which is like related to the cohomology of the loops on the Davis-Januszkiewicz space, but that's a different product, right? Because it doesn't preserve this well, it preserves the multigraded, but it doesn't keep this multigraded component unchanged. So that different product is more related to this labeled configuration spaces, of which this diagonal subspace arrangement complement is only one component. That's exactly what was done by Natalia Dobrinska. But if we are interested in identifying the cohomology ring of this diagonal subspace arrangement complement, then we should proceed in a different way. Well, of course, that is of course suggested by this scheme. That I mean, you need to write down the diagonal approximation for the permutohedral complex, like we and then Litzai did for the moment angle complex and for the cubical. But then the idea was very simple. There is no much choice when you do the diagonal approximation for the cube. You basically, for the cube, you basically just take the square, and then if you want to approximate the diagonal, then you need to make the choice, and it's basically either this way or this way, and then you multiply that. So it's only, and that gives you this Litsai diagonal. But for permutohedral complex, that's an extremely complicated problem, right? So I mean, there were a lot of works of several people, most notably. So yeah, as I said, the product of Celer cochains. In order to define this product, we need this diagonal approximation for the permutohedron. And yeah, that's complicated. So as I said, that was attacked by several people, most notably Sanablidze and Umble in, I think, around 2000. I met with them in Tbilisi, I think, on a conference. They were giving a talk on that, and that came to my mind eventually. Yeah. So that's a way to write down a diagonal for the permutohedron. I mean, I don't have my time is almost up, so it's really hard combinatorial machinery, but I mean it's related to some special sorts of matrices, right? So you can so it's to define it you need maybe 2 or 3 slides. So I mean it's like, yeah, you have this notion of an ordered matrix, which is just you put elements from 0 to q plus 1 into 1 into a matrix in such a way that each row and column is non-zero, and the non-zero entries in this matrix are all distinct, so you just have those non-zero entries, and they increase in each row and each column. That's called the ordered matrix, and this ordered matrix defines you 2 partitions. So the one coming from columns and the one coming from rows in the opposite way, put in the opposite way. So that's one thing. Then you need to consider some special types of ordered matrices in which non-zero elements appear in the consecutive order in each column and row, and also all that like diagonals and subdiagonals contain a single non-zero entry. So example is like this matrix. So you have like 5 elements put into such a way that they increase in each row and column, and then all those conditions are satisfied, right? So that's an example of a step matrix. And then it defines 2 partitions, like that the one is like coming from columns 1, 4, 2, 5, and 3, and the one coming from rows, but that you put in a opposite order 4, 1, 5, and 2, 3. Okay, so then you define some shift operators, but under some conditions I just illustrate that you take this matrix, and if some conditions are satisfied, then you can move this 5 to the right or to the bottom. So that gives you like this shift operators, and that allows you to produce more step matrix from a single one. And then finally, you have this configuration matrix, which you start with the step matrix and apply this shifts operators. And that's what you use in the definition of the diagonal. So that you take the sum is taken over all these matrices with this extra condition, and then you have these 2 partitions, and it splits. It gives you it gives a diagonal splitting. So like, and then you extend it. That's SU. It doesn't stand for special unitary. It's Sanablidze and Umble. Yeah. So yeah. So like this is an illustration how it works for. Yeah, this one is very simple. That is just it. That's this one, right? For the cube, it's a diagonal of the square. But that third one is well, you need to. That's a hexagon, the permutohedron. I need to check that. Yeah, that's, I did. Okay, so. And then the final thing I wanted to say is that like you use this Sanablidze-Umble diagonal to identify the product, and the nice thing about that it interpolates well with this Litsai diagonal, right? So there is a nice projection from the permutohedron to cube, which is, well, I don't have much time. It's just a formula. It maps a face into face, right? This is a so this is on the level of vertices. This is a vertex, right? So that's U1 through UM. It's a permutation, actually. And that's a vertex of the cube. There are some ones and some units there. And yeah, so then you extended this into faces. And then you have this nice commutativity relation that maps Sanablidze-Umble diagonal into Litsai diagonal. And finally, yeah, you have, so that you can guess what you get from the Permutohedral complex when you project it onto a cube. And you get some cubical complex and therefore some real moment angle complex for some different simplicial complex, right? So that's a really interesting family of simplicial complexes that you get in this way. It has some description, but we still have to, we can write it down, but we don't completely comprehend that. So anyway, so yes, thank you. And yeah, it's some references to Litzai, Sonneblitze, Umble, and that's our preprint with Vsevolod. And thank you for your attention. Yeah.